Bismillahirrahmanirrahim. I am Sana Idris. In this semester, I will teach you the subject calculus. Calculus is not a new word for you. You have studied this subject in the previous semester. Calculus, first we must understand what is calculus. Calculus is the branch of mathematics in which we study about the change. Now what change? You can find change everywhere around us. For example, if you move, if you walk, your position is changing. If we study the motion of a car, its velocity, acceleration is changing. We have many examples where force, momentum is changing. Beside the physics, we have many more examples. For example, time of sunset and sunrise is changing. Population of a country is changing. Your age, height, weight is changing. Income of a person is changing. Your marks in a semester is changing. So we have many changes around us. Whenever we want to study these types of changing, we have to consider the subject calculus. There are two main ideas of calculus. One is the derivative, another is the integral. Derivative tells us how fast something is changing, and integral tells us how much something is accumulating or gathered. These two concepts are very different from each other. They introduce at different time and different places, but they are related to each other. In the previous semester, you have studied the derivative in detail. I hope you know all the formulas and concept of derivation. In this semester, we will study the integral in detail. Now first, we must understand what is integral. Integral, it tells us how much data is accumulating or gathered. In order to understand, let us consider a simple example of downloading a movie or a drama. When we downloading a drama, in 1 second some data is gathered. In the 2 seconds, the data will be doubled, while with the increase in the time, there is increase in the data. This information can be shown in the more generalized way in the form of the graph, where time is taken along x-axis and internet speed is taken along y-axis. This shaded area gives us how much data is collected. So the data accumulated or data collected can be replaced by area enclosed. From here on, we will use this word instead of data accumulated. We have many examples where these shaded area or the data will give us some information. Let us consider the example of a car which is in motion. The graph between speed and time will give us the distance. The shaded area gives us the information of a distance, while if we deal with the force and the distance, that will gives us the work. It means in all the cases, the area enclosed gives us the information. But in all these cases, to calculate the shaded area is very simple and easy, because the area is between the straight lines, and you know the formula of a straight line. In this case, we have a square, we have a rectangle, we have an again rectangle. You can calculate the area very easily. And in these graphs, one thing is constant. For example, in this, the speed is constant. Here the force is constant, while in this internet speed is constant. But in reality, it doesn't happen, because when we move in a car, the car cannot move with a constant speed. We have to use the brake many times, so we cannot maintain a speed at a same level. So we have a curve path. In most of the example we have this curve path, and to calculate the area under the curve is a very difficult task. This, in calculus, instead of time and speed, we use like x and f of x. X is taken along the horizontal axis, while its function f of x is taken along vertical axis. Now problem is here to calculate the area along a curve path. We do not have any exact formula like rectangle and square and triangle. Now we have to calculate this area under the curve. Problem is to calculate the area under the curve. We do not have the exact formula, but we can approximate these areas. We have a function which is taken along x-axis. We have x variable which is taken along x-axis, and the function is taken along vertical axis. And we have to calculate the area above the x-axis and under the curve. Simple approximation is to divide this whole area in the form of rectangles. Like here we have made two rectangles, 1 and 2. This is the height of the first rectangle and this is the height of the second rectangle. If you want to calculate this total area, you can make simple formula: area of rectangular 1 here, area of rectangle 2 here, and plus the shaded area which is not here covered in the rectangle. This shaded area is again a problem, but these rectangular we can calculate the area of these rectangular easily by calculating the functional value along x-axis x1 and the functional value along x1 and f of x2. When we multiply it with x and f of x, we get the area of first rectangle, and when we multiply x2 with f of x2, we get the area of the second rectangle easily, because we know the formula of area of rectangle is length into width. Now again the problem is we cannot find the area of the shaded region. Here these are the two shaded region. We cannot find the shaded region because we do not have any formula to calculate this shaded region. But we can reduce these shaded area. How we can reduce this shaded area? If we introduce more rectangles, we can reduce shaded area. If we make 4 rectangles, then you can see these shaded areas are reduced. Again, you have to calculate the area of first rectangle, then add the area of the second rectangle, then third, and then fourth, plus these shaded area. But in this case, these shaded area will be less as compared to this. In order to reduce more these shaded region, let us make n number of strips. If we make these n number of strips, we will be more accurate to the total area. But here again we have a formula: total area is approximately equal to summation I is equal to 1 to n, means we have made n number of rectangles, f of x1 into delta x. Delta x means we have the same width. These all rectangles are the same width, but again we have approximately sign because we do not have the exact area. For exact area, what can we do? We can make infinite number of rectangles. How we can make the infinite number of triangles? When we make the width delta x approximately equal to 0, means very small, infinitesimal width, then the formula will become total area is equal to limit delta x approaches to 0 summation I is equal to 1 to infinity f of xi into delta x. Now we have the solution of our problem, that we have calculated the total, which is the exact area, by making infinite number of rectangles. This looks very great because we have the solution of this problem, but this is extremely difficult, because if you are asked to make infinite number of rectangles manually and then calculate the area of one rectangle, then add the second, and then we get the final result, which is very difficult. I hope no one want to do this. So integration is a solution of this problem. Integration provide us the way to find the area under the curve path where all other method fails. Now, how area and integration are related to each other, we will do this. Relation between the area and the integral. Again, we have the same problem. We have a function and x is the variable of that function. X is taken along horizontal axis, and f of x, its function, is taken along vertical axis, and we have a curve path, and this is the area which we want to calculate, a of x. Area under the curve is equal to a of x, which we want to calculate. Let us consider, let's take the derivative of this function. The derivative of this function is equal to dA over dx. By the definition of derivative, dA over dx is equal to limit delta x over 0 delta A over delta x is equal to, this is the formula of the derivation. Here is the area. Area is always equal to length into width, f of x into delta x over delta x. These delta x are cancelled by each other, and we have a function f of x. It means dA over dx is equal to f of x. Now, the function and the derivative of area are related to each other. This is a relation between function and the area, but in this case we have a derivative of this area. By any means, if we take antiderivative of this equation, antiderivative means if we take if we cancel by d by dx, by any means we get area, and which is equal to f of x and dx, and antiderivative is equal to the integral. So that's why integral is always known as the antiderivative, and it is also known as the reverse process of the differentiation. If one doesn't know how to derivate, the student will not be able to integrate a function. That's why they are related to each other. Integration and derivative, they are reverse process of each other. Now, integration, it provides us the area under a curve path, which was a very big problem before 17th century. It is a reverse process of differentiation, and it is also called the antiderivative, which we have proved in the previous slide. It was introduced by Newton and Leibniz in 17th century. Leibniz introduced the notation of integral like this. This is the notation of integral, where a and b, these are the limits of the integral. F a is known as the lower limit of integration, b is all called upper limit of integration, f of x is known as the function which is to be integrand, and dx is x is the variable of the integration. With the help of this formula, we are able to calculate the area under and between the curves. This very complicated example where we have the area in the three portions, we can calculate easily with the help of the integration. If we have two curves, one curve is this, second is this, and we want to calculate the area in betweens, we can calculate with the help of integration. If we have the area between different lines like this, we have a three lines, one is this, second line is this, and third is this, and we want to calculate the area between these three lines, we can calculate by using the integration method. So integration will enable us to find the area under the curve, between the curve, which was very big problem before 17th century.